joint program seminar between physics department and the CCMS. And it's our pleasure to have Professor Chi-Feng from the NTU Material Science Engineering department. He's a new faculty in this campus. Okay, he just joined NTU in this year, February. Yeah, so 8 months. So very fresh. Okay, and Professor Pai actually graduated from NTU, get his bachelor degree, okay, from the Material Science and Engineering department. He also get a diploma for physics, right? so okay, then he moved to Cornell University and get his PhD degree in year 2014. So now it's just 2 years after his PhD, and he had postdoc in MIT and Cornell, and moved back to NTU. And today he's going to talk about the spin transfer talk, spin talk, the spin orbital talk. I think this your PhD work.
PhD and
some postdoc work. Okay, let's welcome Professor Pai.
First of all, I want to thank CCMS for giving me this opportunity to present mostly my PhD work and a little of my work back at MIT when I was a postdoc. And I have to say sorry because I saw like some of you already, I believe, already heard most of these data or this presentation. So I have to say sorry first. And actually, most of these will be the work that's done in the United States. So not the work that's being done like here after I came back. But for the last part, I will show some progress that I've been doing for the past 8 months. Okay, so here's an outline of my talk. First of all, I will introduce Spintronics a little bit, some historical background, like why we're so interested in Spintronics. I call this a paradigm shift, especially the discovery of spin transfer torque. That leads us to from field control of magnetization to torque control of magnetization. And the status quo of so-called spintronic research or AMRAP industry. That's for this year. And for the second part, I'm going to talk about the spin Hall effect from transition metals. And these are mostly my PhD work back at Cornell University. And I'm going to talk about the spin Hall effect from transition metals, platinum and tantalum and tungsten. And I'm going to show you we can actually use spin Hall effect to switch magnetization efficiently, and especially in this type of terminal device. And for the last part, I'm going to talk about the so-called spin orbit torque, because there was a huge debate between like several different groups that is there only one type of torque coming from say spin Hall effect, or is there any other types of torques? For instance, for traditional spin Hall torque, we call it damping-like torque. But in fact, a lot of people, they also observe the field-like torques, because these torques, in terms of the symmetry, they can be viewed as like effective fields. So we call that field-like torques. And nowadays, people call these two torques, we categorize them together, and we say, okay, so it's spin orbit torque, because they are all coming from a spin-orbit interaction from the magnetic neutral structure. So for the last part, I'm going to talk about these torques coming from magnetic neutral structures, and also discuss a little bit about this theory and are the theories helping at this point. And I can give you the answer now. I mean, no, because experimentalists and theorists, nowadays seems to me that they're working on their own. Like they don't really talk to each other. So I really think that we can improve this community and try to find some connection or common standpoints like between these two large communities. Anyway, so first thing first, before talking about Spintronics, I have to give some introductory, like say, tutorial of Spintronics. And we know Magneto resistance and Hall effect. I think most of you sitting here have heard of these two. And for Magneto resistance, we just like apply in-plane field or out-of-plane field, and then we measure the longitudinal resistance. And for instance, in this case, if we apply in-plane field and we change the direction, and we will see angular dependence of this resistance, and we call that anisotropic Magneto resistance, or AMR for short. And for out-of-plane field, you can apply out-of-plane field, and then you measure the transverse voltage or transverse resistivity. Then this is what we call the Hall effect. And for magnetic materials, if you're using ferromagnetic materials as your sample, then we'll get this anomalous Hall effect, because typically this is the magnitude of this Hall effect is much larger than the ordinary Hall effect. So they call this anomalous. And if you look at the data, it will look like this. So this is the angular dependence, or the angle dependence of MR, and this is the out-of-plane field dependence of the transverse resistivity. So these two are the typical quantities that we will measure if you're in the field of say condensed matter experimental condensed matter physics. These two are your friends. And for Spintronics, I would say the beginning will start from the discovery of GMR. And the reason why I show this paper is because, of course, this is the reason why Albert Ford got Nobel Prize together with, I forgot his name. Yeah, I mean, but nowadays we all remember Ford because he's more active in this field. But anyway, and back in the 80s, they discovered this giant Magneto resistance, and they found that the MR will be much larger than the MR that I just showed you, the AMR in just a regular traditional ferromagnetic material. And I typically show this to my students because this is a very good paragraph that showing that this 6th most-cited physical review letter done by Babbage, I believe. At that time, he was working on this, but at that time, I think magnetic research was generally considered to be a dead end. So I typically use this to encourage my student that if you're working on magnetic materials, and you just need to wait for a longer time to have the next wave. At least that's the case for me. I stay at Cornell for long enough to see the birth of the spin Hall effect research. So typically I'll ask them to just be patient and then wait for bigger results. Anyway, GMR, typically we will show this kind of cartoon, saying that if you have a sandwich structure, if you have two ferromagnetic materials and in between like a normal metal layer, and if the two moments of these ferromagnetic materials they are parallel to each other, and if you send current or send electrons through this junction, depending on the configuration of these two moments, if they're parallel to each other, you'll get low resistance, and if they're antiparallel to each other, you'll get higher resistance. And typically, I think if you define an MR ratio like this, using the difference between the antiparallel state resistance and parallel state resistance, divided by either the parallel state resistance or the AP resistance, you'll get about like a few percent most. 1 or 2 or 3, depends on your materials, choice and depends on the temperature you measure the sample. And another approach is to replace the normal metal layer here, typically we say copper with like weak spin orbit interaction, into like a insulator. This can be, let's say, aluminum oxide. At the beginning, a lot of people use aluminum oxide, or later, people found that if you use magnesium oxide, like MgO, you can actually improve the MR. This is from the tunneling effect, so we call this TMR, even greater than 100%. So I just want to say that, I mean, this number is much bigger than this number. So that's the reason why for modern day MRAM devices or Spintronics devices, we typically want to utilize TMR instead of GMR. And for real-world application, we typically want to pattern these thin films or multi-layers into small devices. And the reason why we want to pattern that into smaller devices is because we want that magnetic layer to be having single domain. So we can see like clear switching. And this is an example from the Cornell group that they pattern these multi-layers or the sandwich structure that I just mentioned into a nanopillar. So this is an SEM image of the top view of this nanopillar. And you can see that the long axis is about like 100 nanometer. And if you send current through it and you measure the voltage between the top electrode and bottom electrode, and then you sweep the magnetic field at the same time, you'll see a small resistance change depending on the configuration of these multilayers. So if the ferromagnetic materials, the moment in these ferromagnetic materials are antiparallel to each other, you'll see a higher resistance. While they're parallel to each other, you'll see a lower resistance. And I want you to see this resistance change is only about 3% or even less. In this case, it's much lower than 1%. And for the magnetic tunnel junction, the one that I mentioned earlier, like if you use MgO, and actually MgO is a secret material. I believe at that time, this group, the Yuasa group, maybe from, I can't remember which university, but anyway, they published this on Nature Materials in 2004, and at the same time, almost the same time, Stuart Parkin from IBM Hamilton also published on the same issue and showing that the MgO tunnel junction can give you a TMR more than 100%. But from what I've heard, Parkin's group already know this material X. At that time, they called this material X for a long time, but they just didn't want to publish it. But anyway, this is a very, very interesting material that you can get TMR even larger than 100%. And the reason why TMR can get larger than 100% is due to its definition. There's no breaking of the physical rules. So this is just a definition of MR. And in this case, actually, in this paper they use architectural growth, so you can see the lattice alignment is pretty good. But in later works, people found that even using sputtering, we can get very good TMR. For instance, in my case, I typically can get more than 100%, around 120%, using standard sputtering system. So this is not, an experiment that's limited to special tools. And more importantly, you can do this experiment at room temperature. For instance, in this case, at T equals to, say, for temperature, low temperature like a 20K, or room temperature, you don't see much change. The TMR ratio is still pretty high at room temperature. And that's the reason why you can see the possibility of building real-world devices out of this kind of tunnel junction. And actually, that's the standard material system for all the MRT devices that you see from major companies. Later, I'll show these company names. But anyway, due to the discovery of GMR and also TMR, we typically would say, okay, we improve the capability of hard disk drive due to the rehash sensor, because now we can use GMR, either TMR, to do the readout, so the signal to noise ratio is much better than before. But that's just one thing. And in the early 2000s, or say late 90s, theorists, they proposed that due to the SD interaction of electrons, so S is from the itinerary electrons and D is the localized electrons, which give you the local moment. They found that through this interaction, you can actually manipulate or control the moment in your ferromagnetic layer through the moving electrons. So the moving electrons, they also have this angular momentum. So when you pass that, for instance, in this case, we consider the same sandwich structure. So the first layer is a ferromagnetic layer, and in the middle you have this normal metal layer, and the second ferromagnetic layer. So it's again a sandwich structure. And if you send an electron from the first layer to the second layer, then when the electron is passing through this first layer, it becomes spin polarized, and it will carry an angular momentum, and this angular momentum can be act on, the second layer. So you will give the second layer an extra torque, and we call this spin transfer torque. And another way to look at this is because if you just consider a single layer of magnetization here, and if you pass a bunch of electrons with a spin which is not aligned parallelly with the local moment, and we know that from the spin filtering effect that the electrons passing through this layer should be having the spin aligned parallel to this moment. So there must be a net moment or torque acting upon this local moment here. And that torque can be phenomenologically described by this so-called Sonsuski LLG equation, or LLGS equation. So for this equation, the former part is just describing the normal, magnetic dynamics in a ferromagnetic layer, which we all seen, like if you learn solid state physics, I believe that you've seen this equation before. So the first term describes the precession of the moment through the effective field, and the second term describes the damping, because in the materials you have energy dissipation, so the moment will start to align along the magnetic field. And the last term is coming from the spin torque that I just mentioned, the interaction between the itinerary electron and the local moment, and the symmetry of this the direction of the torque will be the cross product between sigma. Sigma is the spin polarization direction, and m is the local moment direction, and it will be in this weird cross product term. And you can see that it's also proportional to the current you send in. So the stronger the current, or the stronger the current density, and you will have the stronger torque. And it's also related to the spin polarization value of your ferromagnetic material. So if you have, for instance, if you have a material, ideally, theoretically, you have a material with 100% spin polarization, then you should get a much larger spin transfer torque. And it's also related to MS, like the saturation magnetization of your ferromagnetic layer. So imagine that if you have a material with lower MS, then you can also improve your switching or the torque efficiency. So this is another typical cartoon that you will see if you want to learn about spin transfer torque. They will show you that if you apply a magnetic field, the magnetization, like I just said, will start to precess like along the effective field, and at the same time you have a torque from the damping. But if you apply the current along the correct direction, you'll get a spin transfer torque that's anti-parallel to the damping torque. So that's the reason why we typically will say spin transfer torque is like an anti-damping torque or a damping torque, because the direction is either parallel or anti-parallel to the damping effect, depending on the polarity of the current. So if you apply positive current, say you have the torque pointing this way, and you apply negative current, then the sign will be negative, then it will be acting just like a damping effect. And from that, actually experimental was done a lot of works and tried to really see this. And in the spin valve structure that you just showed, you can apply current, and you can see there's a hysteresis loop, but this x-axis is actually current. So this is not your typical like MR loop. This is a resistance change due to the current that you apply. So that corresponds to this term. So when you apply a larger current, you'll be able to switch the magnetization from one direction to the other direction. And if you apply a current like in the opposite direction, then you can switch it back to its original state. So that's exactly the prediction from the spin transfer torque theory. And this is from a spin valve, like the devices I just mentioned with all metallic structures. So you can see that MR, or the MR ratio, is also very small, or the change in terms of resistance is very small. But if you look at tunnel junction, which is the insulator, the one with, say, MGO barrier that I just mentioned, you can see that the change of resistance is much larger, although it has this weird bias dependence. But you can still use spin transfer torque to switch your device from, say, the parallel state to anti-parallel state, and vice versa. And in order to estimate or try to guess like how large the critical switching current density is, you can use the LLGS equation to derive this formula. And you can see the critical switching current density is proportional to the damping constant, because that's the potential well that you have to overcome, the force that you have to overcome. And it's also inversely proportional to the spin polarization value. So imagine that you have, again, like if you have a material or ferromagnetic material with spin polarization close to 100%, so theoretically you should get a much lower critical switching current density. But in reality, we know that it's not true, because we've done a lot of experiments using, say, the Hoysoil alloy or some alloys with 100% spin polarization. But we know that it's not the case. But in the past, we believe that this is the right equation to describe the critical switching current density. And more importantly, if you look at the term here, it's the critical switching current density is proportional to say coercivity of your ferromagnetic layer, and also the demagnetization field. So because in the anti-damping switching process, you have to pull the magnetization out of plane and then switch it to opposite direction. So if you have I don't know if you have learned like magnetic materials or a basic E&M, you know that if you want to pull the magnetization out of a thin film plane, you have to overcome this large demagnetization field. And at the beginning, people are trying to reduce this term to reduce the critical switching current density. But later, since now people have been working on materials with perpendicular anisotropy, actually they can control this like very easily, and this term can be reduced by a lot. So, but anyway, like if you plug in some typical numbers for, say, damping constant, spin polarization, saturation magnetization for material, in terms of the Dmac field, typically less than Tesla, and you will get a critical switching current density about 10 to the 6 or 10 to the 7 amp per centimeter squared. And actually, this is much higher than what typically people want for real-world memory applications. So people want this to be as low as, say, 10 to the 5th. And I believe that nowadays, like, there are some companies they can provide products with critical switching current density in the high 10 to the 5th range. So I think this is doable. But you can see that the limit is there. So you know the damping constant, you know spin polarization, and you know there's a limit for these fields. So it's more like optimization process, engineering problem. And just want to compare these two types of switching. So like I just said, the first type of MRAM, or the first type of switching is through the effective field, or through the external field that we apply. So in this case, because if you want to generate field using current, then you have to, the field will obey this will be coming from Oersted field. So you have to follow the Ampere's right-hand rule, and that will give you this formula, because your effective field, external field, will be proportional to the current density and the feature size, with the size of your wire. So if you try to shrink the size of your device or near the wire, then the effective field or the external field that you can apply is actually becoming smaller and smaller. So you have to increase critical switching current density, the current density that you send into your device to get the switching. But on the other hand, for spin torque, since the torque is proportional to current density, or the critical switching current density, so this won't scale with the size of your device. So you can shrink, theoretically, you can shrink the size of your device to say 5 nanometers. I don't know, because at that scale, maybe the magneto moment will become unstable. But theoretically, you can shrink the size of your device to some 20 or 10 nanometers. So that's one advantage of using spin torque. You can perform the same switching, but at the same time, you can shrink the size of your device, and that's all what we want, right? For the semiconductor industry, they always want smaller devices such that they can pack more on one chip. And if you look at the layout for field-driven or current-induced field-driven MRAM, which is typically called first-generation MRAM, the cell size will be much larger than the now STT MRAM device, because you don't need an extra line to provide the effective field or the Oersted field in order to switch your device. All you need is the same two-terminal device. So you can do the reading and the writing along the same line, or using the same two terminals to do the reading and writing. But in this case, in the conventional MRAM devices, you need these two to do the reading, but you need extra lines, for instance, this one to do the writing, because you have the same current this way to generate effective field, the Oersted field, in order to switch to magnetization. But in this case, because you are using the torque coming from the other ferromagnetic layer, so you can directly just send current this way. And if you want to do readout, you just send another current, smaller current or voltage, to do the readout. So basically, that's the beauty of this spin torque writing and reading scheme, because it's just very simple. You don't need actual lines to do writing.